Okay, so welcome to lecture 26, I believe. So let's just get right into it. So today maybe we can go a bit overtime also, just to make sure that we can finish off this section, because I think it's also worthwhile to just talk a little bit about some boundary conditions right at the end. So okay, so the proof, it's a subsection, it's the proof of the it's the proof of the graphical decomposition. Okay, so remember B is graphically decomposable, so B is L2 graphically decomposable if B is equal to the graph of a function g restricted to h half plus w plus, where we have that p plus minus is equal to w plus minus plus, sorry, v plus minus plus w plus minus, sorry, I should say L2 here. This is L2. This is just to recall it, right? So this should already be in the lecture notes anyway as the definition. And the w plus minus and the w plus minus star. So what is the w plus minus star? Well, this is exactly the adjoint. So we define it as the adjoint of the projector that say kills this subspace. So what would it be? Minus plus L2. These are acting on L2. These are subspaces of h half, and G is a map that takes us from V minus to V plus bounded linear, with G of V minus intersect h half maps us to V plus intersect h half. And also we have the same for the adjoint. So the adjoint restricted to V plus star intersect h half maps us to, it's contained in now V minus star intersect h half, right? So this is what it means for B to be graphically decomposable. So what we will show is the direction. So today we will show the direction that the theorem that B is L2 graphically decomposable if and only if it is elliptically regular. Okay, so we show B L2 graphically decomposable well, there's subspaces. They have to be the way that I've written it. Well, you can read it off from the way that I've defined the W star. It's not it is a complement, but it's not the complement. I mean, it's the adjoint of the projector projecting to V plus minus, the range of that, yeah. Along this subspace, W plus minus plus whatever. Okay, so we show that B is L2 graphically decomposable if and only if B is elliptically regular, right? So this is what we're going to show in the coming lectures. Okay, so let's start with a lemma. Okay, so the easy direction is when B is elliptically regular, that B is L2 graphically decomposable. We'll tackle that direction first, but before we get onto anything, let's have a look at an abstract lemma. So we have Hilbert spaces H0, H, H1. Densely embedded. So in particular, H0 is also dense in H1. So these are densely embedded spaces. And we have that H0 and H1 are a perfect pairing with the pairing, say, restricted to H or even H naught. So if you put H naught in the second slot, this is just the pairing, the inner product given by just the usual inner product on H. Okay, so it doesn't matter whether we put H or H naught here, because because these are dense embeddings. Okay. Now suppose that H splits into some subspace W plus some other subspace HW, with W contained in this subspace H naught finite dimensional. So the fact that there's a splitting means that there's a projection, so let PHWW be the projection projection to HW along W. Okay, so it means that the range is HW and the kernel is W. Okay, so what happens in this situation? So PHWW restricted to H naught is a bounded projection from H naught back to itself, with the range of HWW of this H naught being equal to HW intersect H naught. Okay. This is the conclusions now. Yes. So maybe then, I should put then in here. Okay. The second point. So the adjoint projector, so P of HWW star, restricted to H naught star, is of course now a projector from H1 to H1. So this star is taken with respect to this perfect pairing, right? Satisfies the adjoint H naught star acting on H1 is equal to now the orthogonal complement of this W with respect to the perfect pairing H naught H1. Right, so the annihilator. So what's this? What am I writing here? Sorry, just give me a second. What have I written here? What am I trying to say? Aha, it's a definition. Sorry, I didn't see it. So HW star sitting in 1 defined to be PW HW why am I defining this to be HW? I think this should be W. So the piece of W sitting in 1 is the adjoint, so this is restricted to H naught, adjoint acting on H1 is equal to HW intersect H naught perp with respect to this pairing. Okay, so the other point is, point number 3, is that if W star, which is equal to, so W star I'm writing as so if W star 1 happens to also be in H naught, then H W star intersect, so have I defined H W star? So I'm going to define this to be H W star 1. Sorry, so this H W star 1 intersect, sorry, this is the normal HW star. So when I write HW star here, this is with respect to just the adjoint projector of L2, right? So maybe I should say that. Then with HW star equals to P HW star acting on H, this thing intersect H naught is dense in HW star 1 and of course the projectors, so then the adjoint projector, so PHW restricted to H naught star, is just now taking the closure of either the projector in H, so this is the star in H, and then I take the closure in H1 as an operator, or I take the closure in H naught, right? So this is where I have this this is where I use the condition of density. Okay, so of course it follows if HW star intersect H naught is dense, then all of these things follow. Okay, oops, that's not what I wanted to do. Okay, so let's have a look at the proof of this. So I know it's a technical lemma, but this will simplify things for us greatly. So what is it really saying? It's really saying that we have a space H naught, we have a space H, and a space H1. And all of these containments are dense embeddings. And it's saying that if we have now projectors in H, they restrict nicely to projectors to subspaces of H naught, as long as we have a nice decomposition of H where one of the subspaces is sitting in H naught. And then we get some nice conditions for the dual projectors. Okay? So that's all this is really saying. Alright, so proof. So of 1, let's see. So the first thing we need to show is that this is a bounded map, and then the space is as it is claimed to be, right? So let's take a U in H naught. If we take a U in H naught, we can just write the U now with respect to this projector plus PW HWU. Okay? But we can just rearrange this now. So PHWWU is equal to U minus PWHWU. H1. It's always with respect to H1. Yeah. So we write it in this way, but U is in H half, and we assume that the subspace W is also, sorry, not H half, H naught, and we also assume that the subspace W is in H naught, right? So this is going to be contained in H naught plus H naught, which is in H naught. And so now we have that this projector, when we take some element from H naught, which is contained in H1, actually lands us back in H naught. And of course the norm is now bounded, right? So PHW WU in H naught is going to be less than the norm of U in H naught plus PWHW of U in, so I should say, okay, yeah, I'll say that in a second. So this is in H naught, and we have that PHWWU is in HW, right? Because it projects to HW. So that implies that PHWW of U is in HW intersect H naught. So that's the first thing. The second thing now is that certainly if we take the H naught, so okay, I should say that before I write this estimate, I should also say that since W is finite dimensional, we have that PWHW of U in the H naught norm is comparable to PWHW of U in the H1 norm, H norm, right? Because on a finite dimensional space, any two norms are comparable. So therefore, I can write this out, and I can take the H naught norm of this, and it's going to be bounded by the H naught norms of these. And of course, this is a bounded projector now back into H naught, therefore we get that this is bounded, right? So that's the boundedness of this, and of course this shows the range, right? So this shows that the range, and we have already seen that PHWWU is in HW intersect H naught. Okay. Okay. So that's that. The second point is also easy, because clearly from a proposition we proved when we were talking about dualities and so on and so forth, PHWW restricted to H naught, taking the adjoint with respect to the reality, to the duality, to the perfect pairing, will give us a projector on the dual on this space, which is dual with respect to this pairing. So I should, okay, I really should, I don't know if I wrote this here, but these should all be Hilbert spaces, right? That's why I'm writing H, Hilbert. The reason I'm assuming they're Hilbert spaces is because then automatically I have everything is reflexive, so that everything is nice and makes sense, and yeah. Okay, so now if we have this, so this is a projector. So this is a previous proposition. I think this is proposition, I wrote 2.62 in the notes. And then we can try and compute the annihilated space, right? So with this calculation has already been done, but let's just remind ourselves. So if U is in W perp H naught H1, so what does that mean? So that means that UW is 0 for all W in W. And this happens if and only if UPW HW restricted to H naught X for all X in H naught. Okay, because that's the range of that map. So this happens if and only if now I can pull the adjoint across PW HW restricted to H naught star UX is, sorry, I forgot the 0 here. I'll put the 0 on this side. 0 for all X in H naught. But H naught is dense in both these spaces. So because it's dense, or it's actually, we don't even need to use that property. We just use the property that it's a perfect pairing, right? So then it tells us that U is in the kernel of PW HW restricted to H naught star, and the kernel of this is precisely equal to PHW W restricted to H naught star H1. Okay, and similarly for HW intersect H naught perp. Okay. So in the interest of time, I think I'll leave the third point as an exercise, right? Exercise. But a hint is that, you know, if you have a U in H1, there exists a sequence UN in H0. And then you can write the sequence UN via the projector. So you can break it up from one via the projector. So then UN is equal to P H0 H W H0 UN plus P, well, okay, this is really, first we take the adjoint and then we restrict, okay, so that requires, that's really where the condition that W star is also sitting in H0 is required, right? So we first take the adjoint, W star H0, this is HW, H0 UN, and then we're guaranteed that this piece, even if we don't restrict to H0, if we just use this projector at the level of H, we're guaranteed that this piece is going to sit in H0. And we have to use that, and then one can show that actually this, the sequence PHW star WH0 UN actually converges to U when U is in PHW WH0 star H1, right? So this is how you would do it. I'll just leave it as an exercise, okay? All right. So we have this lemma. We're armed with this lemma now. So and this lemma is very useful in computing things, right? Because we constantly need to move between. So in application, we have that H is L2, H0 is H a half, and H1 is H minus a half. And we really need to have an interplay between these three subspaces, and that's really where this technical abstract lemma comes in. But before we move forwards, let me introduce a little bit of notation. Okay, so notation, just to make things easier. So for a subspace, say V, sitting in H alpha, you know, it's a very large space, we define the following spaces. So we write V beta to be the V intersect H beta partial M E, and we take a closure now of this subspace in H beta. And we similarly write V check to be where we take the intersection with the H check space with respect. So I should have said early on that all of this is now done with respect to some background boundary decomposing projector P plus, right? So maybe I'll say that here. So throughout fix P plus, which is a boundary decomposing projector. Okay. So this is with respect to, this is where we, well, okay, the D space we don't have to worry about too much because it can be described by any projector, but where it really matters is the hat space. So this is with the H check P plus of D. And the hat space, of course, now requires the P plus, right? So this P plus of D closure with respect to the hat space. So these are the notations that we will fix. And also I'll recall, and this is from before, so this is alluding to the question that was asked earlier regarding this W star and its definition. So we've already used this before, but if we have, if B is equal to B1 plus B2, these are Banach spaces, so there is a projection, then, the adjoint space is B1, or some adjoint space, as if we have some duality, is going to be B1, B2 star, and we write B1 star to be equal to P B1 B2 star of B star, right? This is the notation from before, right? I should say, well, maybe I should say B tilde, where we have a perfect pairing between B and B tilde and reflexive. I should say reflexive, okay. All right. So now let's have our first proposition in this direction for proving the required statement. So let P plus, well, we've already said that P plus we fixed to be a boundary decomposing projector. So I won't repeat that again and again. Suppose that V plus minus plus W plus minus is equal to P plus minus L2 ME, with W plus minus and W plus minus star in H a half finite dimensional. Okay. Then I want to make some assertions. So the first thing is, so now we have a projection, right? I mean, we have L2 splits into V plus W plus and V minus plus W minus, because this is a boundary decomposing projector. So all of L2 is equal to P plus P minus. So now we have the projectors V plus minus W plus minus plus V minus plus let me see now. Why do I only have V minus plus there? That's a bit strange. It should be P minus plus L2. So this restricted to H half is a bounded projector from H half. So this descends to a bounded projector from H half to H half bounded projector. Okay. 2. So this also then follows. So H half ME is equal to V minus alpha plus W minus plus V plus alpha plus W plus, which is equal to V minus star alpha plus W minus star plus V plus alpha star plus W plus star for alpha negative half. Okay. And the third point is that V plus minus a half is dense in V plus minus minus a half, and V plus minus star a half is dense in V plus minus star minus a half. Okay, so the proof of this So it follows from the lemma, right? But we have to noting that P plus minus, remember in the assumption of, well, at least for P plus, the assumption was that P plus restricts, if we restrict this to H alpha, oh sorry, I should say H beta, this is a bounded mapping from H beta ME to H beta ME in the range beta from a negative a half to a half, right? This is a bounded projector. Of course, then 1 minus P plus will also satisfy that, the complementary projector. And that's really what needs to creep in, because we have a subspace here which is P plus minus of L2. And we need to know that when we intersect that space with the H alpha or the H minus alpha, if we close it, that we get the right spaces back, right? So that's the only thing to note. So it just follows from the lemma, and I'll leave the details as an exercise. Okay, so that's actually a good exercise to do. All right, so let's now prove one of the directions, right? Proof of B elliptically regular implies BL2 graphically decomposable. All right, so first of all, let me introduce another small piece of notation. So for V, a subspace of H alpha ME, I want to write V perp H minus alpha to be the annihilator with respect to the pairing, of course, H alpha H minus alpha induced from L2, and similarly for V perp H. So if V is in H, check P plus of D, we want to write V perp H hat P plus of D, and when V is in H hat P plus of D, maybe we want to write V perp H check P plus of D with respect to, remember we have a pairing. Okay, maybe I should have explicitly said that. I don't know why I missed it. Maybe I'll say that later on. That would have been a clever thing to fast forward to here. Maybe I can still do that. Yes. Before I introduce this notation, let me introduce a quick lemma. So the first lemma is that the L2 pairing in a product extends to a perfect pairing P plus minus star H half ME P plus minus H so I should say this is a half and this should be a minus a half ME and P plus minus H minus a half, no, star minus a half ME, perfect pairings between these spaces, H a half now ME and also a perfect pairing between, well, all these perfect pairings, right? H check P plus D, H hat P plus D, and also V plus star, V plus minus, and W plus star, W plus minus, as in previous lemma, right? So under the hypothesis of the previous lemma, this is true. Right. So maybe I should write this a bit cleaner. So this is what, so actually the proof of this follows exactly as before, right? We had an abstract lemma that allowed us to exactly assert when we have these perfect pairings, when they descend down to the level of subspaces when we have projectors. And before we applied this to the spectral projectors, but it makes no difference whether we do the spectral projectors or not here. And also actually these spaces, so it's a whole list of spaces actually. So we have these, and we also have this sort of thing, right? We have star, a half, minus a half, and V plus minus a half. And we also have V plus minus star a half, and V plus minus minus a half. So basically everything you want becomes a perfect pair, and it just comes out of the wash. So that's at least what allows us to make sense of this annihilators now with respect to the perfect pairing that we have with respect to the spec given by the boundary decomposing projectors more generally than the spectral projectors. Okay. All right. So let's get back to the proof of this. So now, so the proof. So by assumption, so what does it mean for B to be elliptically regular? It means that B is a boundary condition, so it's a closed subspace of H check, but it's also contained in H half. And we have that the adjoint boundary condition is also sitting in H half. Sorry, this is the wrong direction. I'm really sorry. This is the harder direction. Sorry. This is that if we have a graphical decomposition, we end up getting a elliptically regular boundary condition. So B elliptically regular implies B. B L2 graphically decomposable implies B elliptically regular. That's the direction we're proving, right? So by assumption, we have that B is in H half by assuming the graphical decomposition, right? So so what we need to show for the boundary condition to be elliptically regular is that the adjoint boundary condition is in H half. But that's equivalent to saying that the annihilator in the H check space is sitting in H half, right? We need B dagger to be in H half MF, but this is equivalent to be annihilated in H check P plus of D sitting in H half of dm of E. Okay, and that's because we have this perfect pairing, and because we can describe now boundary conditions with respect to the P plus. Okay, so so the first thing to note is that by using this last proposition and also the lemma from before, we can compute the annihilated space of the W's, right? So the W's are finite dimensional. So we note that W plus minus perp, so these are sitting in H half. So I can consider the annihilator in the larger space, which is H minus a half, right? So I annihilated in H minus a half, and this is going to be W plus minus star plus V minus star negative a half plus v plus star negative a half. Okay, so of course we can write here, you know, w plus minus of the projector acting from, you know, acting at the level of h minus a half. But remember, the w plus minuses are a finite dimensional space. So taking a closure with respect to the h minus a half norm is not going to alter anything, right? The h half spaces remain fixed. Okay, good. So now, so we have a graphical decomposition, right? So B is, I should really maybe say here that B is equal to graph of G restricted to h half plus W plus, and this is now sitting in h half. So we've now looked at, so if we want to compute the annihilator in h check, we first compute it in h minus a half and intersect with h check, right? That's the name of the game. So we want to now compute the annihilator of B here in h minus a half. So we compute the annihilator of the W plus and then the graph. Okay, so now we move on to the graph. So we take V plus GV such that V, so little v is in big V minus a half. And we annihilate this in h minus a half. Right, so what are the mapping properties of G? So G maps, so maybe I should have recalled here. Oops. Maybe I should have recalled that. So what does, so L2 is equal to V minus plus W minus plus W plus plus, V plus plus W plus. And the G maps from V minus to V plus, right? So when we annihilate this, what are we going to pick up? We're going to pick up W minus star, and then we're also going to pick up W plus star. Good. And now we're going to pick up the adjoint of the G, right? So now we have U minus G star of U, with now U coming from V plus star minus a half. Okay. Right, so now if we write down the annihilator of B in h minus a half, so this is going to be the annihilator of W plus h minus a half intersect the graph of G restricted to h half annihilated in h minus a half, because ordinarily there are some, right? So there are some, and so the annihilated subspace is going to be the intersection of the annihilators of these subspaces. So what's that going to be? So so if we look at the W plus, we have a W plus here, and we have the V minus and the V plus. So it kills hang on, this doesn't look right to me. This is W minus plus, sorry, minus plus, right? Because, I mean, if we take the annihilator of this, we're not going to pick up the W plus star space. We're going to pick up V plus star, W minus star, and V minus star, right? So this has to be spun around the other way. So this is now going to contain the W minus, but it's not going to contain the W plus. So what we end up with is W minus star plus U minus G star of U, such that U is in V plus star negative a half. Okay? So that's when we annihilate in H minus a half. So now let's have a look at what happens when we look at the subspace, which is the hat space. Okay? So now we look at B annihilated in the hat space P plus of D. So this is now equal to B annihilated in H minus a half intersect the hat space. Okay? And so what happens? So this is going to now be so let's explicitly write this out so we can see how this comes about. So this is now going to be P minus H minus a half partial m e plus p plus h half partial m e with adjoints, of course. Okay, so that's the hat space. So the point is that here we have h half regularity in the plus side, right? So because we have h half regularity, so the w minus is sitting on the subspace of the p minus, and then we have the v plus sitting in the p plus subspace, and the graph G is mapping from the v plus to the star to the v minus star. So this is precisely now going to be w minus star plus u minus g star of u, such that v plus star of a half. Okay? But we assumed that g star maps in the graphical decomposition. One of the conditions is that the g star maps us from v plus star half to v minus star half. So it means that, so if we take the u here to be in the v plus star half, then we're guaranteed that the g star u is also in h half, right? So this is now, so together that means that this is now contained in h half me. Okay, since g star of v plus star half is contained in v minus star half contained in h half me by assumption. Okay, so that's the easy direction of the proof. So any questions so far? It unfortunately takes a while to get used to a lot of these calculations with subspaces. So, you know, when Christian and I worked on this, we really, I mean, maybe he was more used to it. I'm not, but I certainly spent a massive amount of time having to really work through these calculations in detail and checking everything with projectors and not just calculating as if they were subsets, because then you can really, you know, get into trouble. I mean, all of these things have to really be verified because it can be very tricky when you have subspaces and when you have subsets. Okay, so it has to be a half, because otherwise we will never end up in h half. Right? Okay, so the opposite direction is considerably more difficult, right? So opposite direction is considerably more difficult. So let's have a look. So the proof now is going in the direction of B elliptically regular implies a BL2 graphically decomposable. So the point is that we need subspaces now, right? We have to construct the subspaces, the V plus minuses, the W plus minuses, etc. So let's do that. So now we have to define the following subspaces. So the way that we do it, I mean, we have so B elliptically regular means that we have B and the annihilator of B in the H hat space. These are both sitting in H half. Okay? So the point is that we have, remember, we have L2 equal to W minus plus V minus plus W plus V plus. And then we again have, we can write this now as, so L2 is again written exactly, well, I'll omit that, W plus star plus V plus star. So the point is that we're going to first define these spaces, right? We're going to define the spaces, well, let me see. So we're going to define these spaces here. So W plus plus V plus, and we're going to define these spaces. Oops, minus star plus v minus star. And then we're going to use projectors to push between these spaces. Okay, so we obtain the remaining spaces by using the adjoint projectors. Okay, so let's see how that works. So define the W minus star to be the P minus acting on L2 ME and intersected with B annihilated P plus of D. Okay, so immediately you can see that this will be a subspace of H a half, because the B annihilated in the check space will be in H half. But we'll talk about these quite thoroughly in a moment. And now I'm going to write the P plus of L2 ME intersect B. Okay, so again, B is in H half, so the subspace W plus has to be in H half. Of course, we have to assert that they're finite dimensional, right? And that will come. V minus star we define as P minus star L2 ME intersect W minus star annihilated now in L2. Okay, and now we have the V plus star, V plus, which is given by P plus of L2 ME intersect W plus annihilated in L2. Okay, so this is really the annihilator of the space W in P, either P minus star L2. I could have just directly put P minus star in there, but I just wanted to really explicitly write out what's happening. So now that we've defined these pink spaces, we're going to define these white spaces, right? So so now we write W minus as equal to P minus W minus star. W plus star I'm going to write as P plus star of W plus. And then the V minus I'm going to write as P minus of V minus star. And the V plus star I'm going to write as P plus star V plus. Okay, so we have projectors. So we have projectors here. This is P minus L2, and this is the P plus, etc. So what I'm really doing is I'm pushing via the projectors from the V minus star to obtain a space V minus. Okay? And of course we have to make sense of all of this, right? So we have to make sense that we have to ensure that all of this makes sense. So for that purpose, let's have a look at this following abstract lemma before we proceed. We need a number of abstract lemmas that will allow us to compute things. So let H be equal to H naught plus H1, and this is again equal to H naught plus H1, say prime. I'm not assuming anything orthogonal here, okay? But we have such a splitting. Then the claim is that the projector that projects to H1 along H0 restricted to the subspace H1, which takes me from H1 now to H1, sorry, there's a prime here, is a Banach space isomorphism. i.e. it's an isomorphism which is bounded, so it also has a bounded inverse by the open mapping theorem, right? Because the spaces H1 and H1 prime are closed by assumption. So this is actually a good thing to attempt to prove. So I'll leave the proof as an exercise. Another fun little thing to prove is the following. So let B1, B2 be Banach spaces such that, so we have a dense embedding well, we have an embedding of it doesn't need to be dense, sorry. We just have that B1 is continuously embedded in B2, right? So we have that the B2 norm is now controlled in terms of the B1 norm for all U in B1. Okay, so if now B3 is a subspace of B2 is closed, then B3 intersect B1 is closed in B1. Okay, so I'll also leave this as an exercise because it's straightforward, but it's an enormously useful lemma, actually. All right. Now let's have our first proposition in the direction of this graphical decomposition proof. So, okay, so by hypothesis we have that, so by hypothesis, so we recall, well, maybe I'll write it before the proposition. Recall that by hypothesis, B and B perp H hat P plus of D, these are both contained in H half. Okay, so the proposition. So now throughout we're going to fix the spaces that we had before, right? So we're going to the spaces, whenever I refer to W plus, V minus, etc., etc., it's going to be those explicit spaces that we constructed. So P minus, so the first thing is that P minus B, so the negative spectral projector, the negative, the complement of the boundary decomposing projector acting on B, and P plus star of B perp H hat P plus of D are closed subspaces of H half partial ME. The second point I want to say is that W plus minus and W plus minus star are all in H half and finite dimensional. Okay, so we're getting towards what we want. The third thing is all spaces we have defined above are closed in L2. And the last point is that P plus minus L2 ME is equal to V plus minus plus W plus minus, and P plus minus star L2 ME is equal to V plus minus star plus W plus minus star. Okay? So this is one of the key propositions that we need in order to really, one of three key propositions we need in order to really to make this thing happen. Okay. All right. So let's see how we're going now. Yeah, actually, we're not going bad. Okay. So proof. So B is a subspace of H check P plus of D closed, since it is a boundary condition, and also by hypothesis B is a subspace of H half of ME. So by lemma, we have that B is actually closed in H half ME. Okay? Since H half ME is densely contained in, well, it's not only continuously embedded, but it's densely embedded in the check space, right? Continuous dense. So now we have a closed subspace of H half, and we have a closed subspace of this H check. So we can just consider the inclusion mapping. The inclusion mapping is a bijection. It's a continuous bijection because it's contained continuously and it's dense, and so therefore the inverse map, which is of course again the identity, must be continuous. So what does that really tell us? So therefore, considering B with respect to the H half norm, mapping to B with respect to the H check norm is given by continuous bijection. So the open mapping theorem says that the map has a continuous inverse. But what is this map? The map is just the identity, right? Therefore, we get, so what that is exactly saying is that the H half norm is comparable to the H check norm for U in B. Okay? Right. So why is that important now? So hence, what can we show? So we have U H half, and this is comparable to H check P plus of D. And what's this equal to? So this is comparable to P minus of U H a half plus now P plus of U H minus a half. That's the description of the check space with respect to the boundary decomposing projector. So what? So then the point is that P plus, so one of the hypotheses that we had was that P plus preserves regularity, right? P plus maps H beta to H beta when beta is between negative a half and a half. So P plus in particular maps B, which is contained in H half, into to H half, but of course we're now looking at the norm in H minus a half, but H a half maps into H minus a half compactly, right? So we factor P plus through this map, so i.e. P plus mapping, P plus restricted to B, mapping B to H minus a half ME is compact. So now we have a lemma, right? So we have this lemma from before that says that, from Hermander, that says that if we have a U that's bounded above by some function L mapping to some space and a compact map K, then we can conclude that the map L has finite dimensional range and, closed range and finite dimensional kernel. So by previous lemma, we obtain that the range of P, B, which is exactly P minus B, is closed in H a half, and that now the kernel of P minus restricted to B is what? So this is the U in B, such that P minus of U is 0, and that's exactly equal to the U in B, such that well, P minus of U, so that's saying that's the same thing as P plus of U equals to U. So, well, U in P plus of L2 of ME, right? That's what it is. And that's equal to B intersect P plus L2 ME, which is what? That was the definition of our space W plus, right? So this is finite dimensional. Okay, so we can calculate exactly as this, as we have done for the P plus B star. So similar calculation for P plus star B annihilated H P plus of D, but now we have to replacing H check P plus of D with H hat P plus of D, etc. Right? So we make the changes that you need to make, and then you get what you want. So this proves, so far we have proved, this proves 1 and 2 partly, and a part of 2. i.e. we've shown the W plus and the W minus star are finite dimensional and containing H half. Well, they're containing H half, but the finite dimensionality, right? Okay. P plus B star, sorry, P, similar calculation 4. Oh, replacing. Yes. Okay. So now let's have a look at the next thing that we need to do. So let's look at L2 of partial ME. So this is going to be P minus L2 of partial ME plus P plus of L2 partial ME. We already know that, right? It's a boundary decomposing projector, but we also have that this is now going to be equal to P minus star of L2 partial ME. So if we calculate the orthogonal complement to the P plus L2 partial ME, we exactly get P minus star, okay? So this is the orthogonal complement now to P plus L2 ME. Okay, okay, maybe I should have done it the other way around. Well, alright, P plus star. No. Let me see. What do I want to do? I want to put. So what did we construct? We have W plus. We want to push. Yes. Okay. So then from the previous lemma, so by previous lemma, we have that the P plus star is an isomorphism from P plus of partial ME to P plus star L2 partial ME. Okay, this is an isomorphism. So what do we get? So then, therefore, W plus star is equal to P plus W plus is finite dimensional. And we have that W plus star is containing H half, ME, since P plus again maps H beta to H beta for beta in the range -0.5 to 0.5. Okay, so that's really good. Moreover, well, we have actually that the dimension of the W plus and the W plus star and the W plus are also the same, right? Well, maybe I don't need to write that. Similarly, for W minus star, W minus, which is equal to P minus star of the W, P minus of the W minus star. Okay. So now this really proves 1 and 2. This yields 2. All right. So now for the next point. Next, note that L2 is also equal to what? W plus W plus perp. Okay, we're in Hilbert space, so we have the orthogonal complement, right? And we always have a projection along a subspace and a closed subspace and its orthogonal complement. So now, for U in L2, U in P plus L2 partial ME. So if, well, 4, we should say 4. For U in this space, we can write this along with this projector, right? So we can write W plus perp U plus W plus perp W plus of U. And so now we just subtract again. So we do the trick that we saw before. W plus perp U is equal to P W plus perp W plus. Okay, but by construction, W plus is a subspace of P plus L2 partial ME. Okay? And therefore, PW plus perp W plus, there's a U here, of U is in what? It's in W plus perp, because that's the range it maps to, intersect P plus L2 of partial M of E, but that's exactly equal to V plus. Okay, so that gives us that P plus of L2 partial ME is equal to V plus plus W plus, and similarly we get it for the others, right? Similarly, P minus star L2 partial ME is equal to V minus star plus W minus star. Now, to get the remaining spaces, it suffices to note that P plus minus L2 partial ME to P plus minus L2 partial ME are isomorphisms. So these and of course the P plus minus star, taking us from P plus minus L2 ME to P plus minus star L2 ME are isomorphisms, and so remaining equalities or remaining decompositions hold. So conclusion follows, I should say. Okay, so it takes a little bit of doing to try and organize all of these spaces to nicely and neatly fit in together, right? So that's really one of the fundamental points about this about doing this whole thing. So this is the first key proposition we need in the proof. Any questions so far? Before we move on to the next one. I think we can do the next one in the next 15 minutes. Okay, if not, let's move on. So the next proposition, so now let's just quickly have a look at this proposition again, right? So in this proposition, we've claimed that P minus B and P plus B of this annihilated space are closed subspaces sitting in H a half. We also have some other spaces here, right? We've also constructed all of these other spaces. So we need to somehow connect the spaces P minus B and P plus B, which comes out of the wash from the boundary condition, to, I mean, the W pluses and the V minus star and so on and so forth only contain finite dimensional subspaces of the B. So the majority of the B and the annihilated subspace of B has to sit elsewhere, right? That's where this graph comes in. So we have to really connect these V minus, V plus, V minus star, V plus star spaces now with the remaining parts, right? And so we can see from this the construction that the majority of it is gonna, the largest piece of the boundary condition B is really going to be contained in the P minus B and the P plus star B annihilated. So we need to connect this somehow with the V spaces. And that's what the next proposition gives us, right? So this is step number 2 in the proof. So P minus B is equal to V minus a half, and P plus B, well, there's a star here, it's missing in my notes. Annihilated H hat P plus of D is equal to V plus star half. So this is really a key observation in all of this. Okay, so we're going to prove this in F steps. So the first thing we're going to prove is this claim. The W minus star is equal to P minus star H minus a half intersect with B annihilated in H minus a half. Now that sounds really crazy because we've made the space very, very large, right? But let's see why this is true. This is really true because the intuition here is that the interesting part that really contributes to the W minus star is actually not in the P minus piece, right? The majority of the interesting part of the B perp is really sitting in the positive side and not the negative side. So the negative side is so sparse that even if we expand the space when we intersect, we end up getting just the original space, which is quite small. Okay, so clearly, so the direction is clear, right? Because we define the W with the L2 in place of the H minus a half. So let's now consider the reverse. So we prove reverse. Okay, so let U in P minus H minus a half partial ME intersect B per H minus a half. Okay. Sorry, P minus star here. Okay. So in particular, U is in H check, H hat P plus of D, right? Because if we're in the P minus a half piece, P minus a half is a subspace of the H hat space, and now we're in a subspace of that. So certainly we're in this space. So that means that we can now intersect everything with the H hat. So therefore, U is okay. Okay, so I'll say that. But P minus a star H minus a half partial ME intersect B H minus a half is then equal to P minus star H minus a half partial ME intersect B H minus a half intersect H hat P plus of D. But then this is the annihilator now of B in the check space, right? In the hat space. So this is minus a half partial ME intersect B in the hat space. But by assumption, the hat space is in H a half. But by assumption, we have that B H hat P plus of D is actually in H half. So that means that this space is actually contained now in well, it's contained in P minus star H a half of partial ME intersect B perp H check P plus of D, which is certainly contained in W minus star, right? So that's how it goes. Okay. So it looks a bit iffy, but as I was saying, the main point here is that since we are sitting in this P minus a half piece, we're guaranteed to be in the H hat. And because we're in the H hat, by assumption of this being an elliptic boundary condition, elliptically regular boundary condition, it means that this annihilated subspace is sitting in the H a half. Okay. So P minus B now annihilated in P minus star of H minus a half, we claim is equal to W minus star. Okay, that's the second claim, right? So maybe I'll write claim here. And I'll put a tick here, so that's the second claim. So W in W minus star. This happens if and only if W is in P minus star H minus a half, so using A, right? And we have that WB is equal to 0 for all B in B. Okay, and this is now the annihilator in H minus a half, right? So we're doing all the annihilations now as a consequence of B in H minus a half. This occurs if and only if W is in P minus star H minus a half, and we have that P minus star WB is equal to 0 for all B in B. So now we have, again, this is going to occur if and only if we're in H minus a half. And now I'm going to pull the boundary, the projector across. P minus of B for all B in B. Okay. So this occurs if and only if we have W in P minus star H minus a half. And now, so now we have P minus B here. So WV equals 0 for all V in P minus B. Okay? So this is going to happen if and only if we are in W is in P minus star H minus a half ME intersect. So now I'm saying that it's in the annihilated subspace of P minus B, annihilated in H minus a half. So now this is exactly the same as saying W is in P minus B, annihilated in P minus star H minus a half partial ME. Okay, well maybe I'll omit that. Okay, so that's an easy calculation. Sorry, we're almost there. Actually, I don't think we'll be much over time today, maybe just 5 minutes. So now the point is that we have P minus of B is equal to W minus star annihilated in P minus H half ME. Okay? So this is immediate, right? Immediate. Since, well, we have that we mentioned that P minus of the half and the P minus H minus a half are a perfect pairing. Okay? So we already have this. Okay, and all right. Now let me have a look. So now we have what? W minus star perp. Now I want to annihilate this in P minus H a half. So the claim, okay, I should say this is a claim, right? These are all claims, so maybe write claim here. Okay, I'll omit it in the interest of time, but these are claims. All right. Claim. So the W minus annihilated in the P minus, I claim this is equal to W minus star annihilated in L2 intersect with P minus L2 ME intersected with H half ME. I mean, that's also immediate, right? There's really nothing to do there, because if I want to see how much of the annihilator is contained in the P minus, first I annihilate it in the larger space L2, then I intersect with the subspace, and then I intersect to get the right regularity. Okay, now claim E. So the claim, so this is a crucial claim. So W minus star in perp L2 intersect P minus L2 ME. The claim is that this is equal to P minus of taking this annihilator in L2 intersect with P minus star L2 of ME. Okay, so we annihilate in the P minus part, and then we push down with the projector P minus. Okay, so this has two directions. So let U be in this space. P minus W minus star perp L2 intersect P minus star L2 ME. So and let U prime be in so therefore U is equal to P minus U prime, where U prime is in this space, right? U prime is in here. Okay. So now we need to show that it's actually that U is in W minus star annihilated in L2 intersect this P minus, right? So let W be in W minus star. Then let's have a look. So then for WU, this is equal to U P minus U star, and this is equal to now, sorry, this is W, P minus star W U prime. But the P minus star W, I mean, remember the U the U prime is also in the W minus star annihilated space, right? So certainly, because I've taken W minus star, which is a subspace of the P minus star, this remains fixed. So this is just W U prime, but by construction, we assumed that from the condition that we have that U is in the annihilated subspace of the W. So this is certainly 0. Okay? So that implies then, and this is for all W, we have that U and W satisfy this. So this tells me that U is in W star perp, W minus star perp L2. And of course, by construction, I mean, we assume that U is equal to P minus of something, right? And U in P minus L2 partial ME. Okay, so that certainly shows the containment that whenever we're in here, we're in here. Okay, so for the other containment, sorry, I'm only going to take a few more minutes. I'm almost done. So for the other containment, so let U now be in W minus star perp L2 intersect this P minus L2 space. So we know from before, from previous lemma, so previous lemma gives U star in P minus star L2 ME such that U is equal to P minus star L2 of U star. Okay, so we have this because of the way that the spaces sit. Okay, I really have to go to the next page now. I'm sorry. All right. Okay. So now for W in W minus star, so we need to now show that the U star is annihilated in the right way, right? So we automatically have this for the U, right? So we have U W minus star is 0, but what is the U equal to? So the U is equal to P minus of U star W minus star. But then we did as we did before, and we pull this across W minus star. Sorry, I don't know why I wrote W minus star here. I'll just write W. And of course, W is in a subspace of the P minus star, so it keeps it fixed. Right? So that implies that actually U star is in W minus star perp L2, and we have that U star is in P minus star L2 of ME. Therefore, we have the reverse containment, right? So I think it's easy to see that we have the reverse containment. Okay, last point. It's just a few more lines. So now we really prove what we want to prove. So what is PB minus? So the claim is, so now the claim, we finally prove that PB minus is equal to V minus a half. So how do we do that? So P minus B, so the first equality we get from these conditions that we've proved, you can look up which one exactly because I didn't write it down, unfortunately. We can write this as the annihilator of the W minus star in the P minus H minus a half. Okay? And now we can write this annihilator as we did before as the annihilator in, sorry, not minus a half. So now this is the annihilator in L2 intersect P minus L2 intersect H a half ME. Good. And now we replace this by just what we proved, right? So this is P minus W minus star per L2 intersect P minus L2 ME. intersect h half me. But what is this? Well, this space is exactly the space v minus star, right? So this is equal to p minus v minus star intersect h half partial me. But that was the definition of the space v minus. So this is v minus intersect h half me, and that precisely is v minus, the definition of v minus a half. So the claim, okay, so that ends that. So the claim that p plus star be annihilated h d pd equals v plus star a half follows by mimicking this argument mutatis mutandis. Okay, so thank you for your attention. Sorry for taking a little bit more time. Next time we will really be able to give the full proof and also discuss some boundary conditions. And then we will end the course on a happy note. Thank you so much.